all set except
Except,
one thing we don't have is participants here at this class, they don't see it.
I can do screen mirroring.
Okay. Now look at that. To make it even more professional, I have two mics.
You can start recording your own podcast.
Don't put that kind of ideas in my head because I can get excited about it. Okay, so
So how does the, oh. Now
how is the
this-
quality? Quality is great.
Now this,
But now you
something
hide
went wrong
something.
because I did this, the mirroring.
Mirroring,
Now
Okay,
the
so let me
size
see.
doesn't fit.
size-wise. Ah, this one.
Yeah.
Okay, because I lock this, so I need to unlock this.
Yeah. So if you make that bigger, then the audience can also enjoy. Yeah, that's good.
This size.
Yeah, that's perfect.
All right.
Yeah.
And I'm gonna lock it again.
But it's a little bit off, like it's not centered.
It's not centered. But
No,
not
it's-
much. It's okay.
It's okay. It's okay for me.
So,
That's
but
good,
how is
but
that? How is that? What is it there online? But this, where is your what next?
So here's my.
So they see this.
This is what they see.
Okay. Can you make
Oh.
this as a?
Yeah, yeah. I'm gonna make this bigger. So I'm gonna.
It might change things here.
Let me see. If I don't want to blow it up all the way.
You can make this to the max size.
Really?
Yeah. How is it? Now, Mustafa, how it look?
Still same field.
Same.
Oh, that's perfect.
No, it's like he's cutting something.
Yep, he's out of the picture. Like you can, I believe that you can extend it.
Cycling. So it's okay. So I'm gonna do like this.
Yeah.
Escape.
Yeah.
And we need to go back to
Yeah. that
this
one.
guy. And was this a window capture?
Yeah, it's a window capture.
This is okay.
Yeah. Unlock it.
And we're gonna move it because it was like, so we're gonna move it here because it's gonna be,
Yeah.
Yeah, now it's better.
Okay.
all right, and then we're gonna put this out, where is it, this again?
What do I look?
PowerPoint, your PowerPoint.
Yeah, yeah.
Okay, you just put it on.
Lock it.
Yeah, you don't, yeah, you can lock it to make sure that it's not making anything funny.
Yeah, and then we go to this guy. And
Yeah.
we maximize it.
Maximize it. And then,
Oh,
and how is it?
Takes a few seconds. No, like believe that you have to
I did that.
redo everything. Like for the
Redo.
No, like right. You have to share your screen, not just the PowerPoint file.
Okay.
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 So this is the problem, is this one.
Okay. So we make this smaller again. And now here, yeah, you say.
So you wanna share what?
The screen, like I don't know. Like I'm a Windows guy.
Okay, so we do this.
Yeah. And then yeah. Okay. Yeah. That's okay.
There is no such thing like,
Yeah, yeah. If you do decrypted
no, it should be
Capture screen.
capture, but I don't see,
capture.
where you see, there, capture card,
No.
browser,
If you do Mac OS screen capture,
Yep.
yeah, do that. Yeah, that's okay. Yeah, there you
okay,
got
now I think it is okay.
it. Yeah,
All right, then we're gonna lock this one.
yeah. And then we go to. Oh, really on the thing. Yeah.
Yep.
And now we go to the PowerPoint.
But
Okay.
you are not in the picture.
Okay, so we need to put ourselves in up top, one more thing.
Yeah. Yeah.
So video, order, can you see the order somewhere? Order,
Yeah.
move up.
Okay.
No, it's back
Yeah.
in, back here.
But can you move yourself to the corner?
Sure, I
Because
can.
right now you're in the center.
Yeah.
Yep, okay, and then Last click will be, where was it? This one.
This one. Yeah,
And you
then,
maximize it.
and play.
Yep.
Perfect. Okay, guys, finally, we are good to go. Today is something a little different. We're going to have a special guest in today's lecture. It is a visiting professor from LUT University, Arend Schwab. He's originally from Delft University. As you can see that this is a double affiliation, Delft University and LUT University. And this lecture is about bicycles, bicycle dynamics. This is something that Arend is very good at. So he knows bicycles back and forth, and he's using bicycles in his daily life. This morning he came to university by bike, even though the weather condition was challenging. But he made it happen. But now we're going to learn something fun that is related to bicycle dynamics, and what is that the science can do for cycling. All right. Thank you. And we're going to close, because today is a little bit of a special day. We're going to close roughly 1 hour from now. Okay?
Okay, Aki, thank you for this nice introduction. So my name is Arend Schwab. I will point to this screen, I think, yeah. Or I use the pointer here? No. For the audience here, I will point, and in the live stream, that's what it is. So Arend Schwab, I'm going to talk about the art and science of cycling. I'm a professor emeritus from Delft University of Technology. But well, I like to keep working, and I'm a very good friend and colleague of Aki for many, many years within the Multi-Body Dynamics Society. And Aki was so nice to give me an affiliation here as visiting professor. So I spend in Finland about 4 months a year. I like winter, so therefore I'm here in March. But I'll be back in June, July, and August. So if you want to meet me, come to my office. It's 6609, or send me an email, or my email you can easily find. Type my name, Arend Schwab, in Google, hit I'm feeling lucky, and all the information is there. And I really encourage you to step by if you have questions related to this presentation, or any questions on your studies. Like, I want to do an internship in Zimbabwe. Do you know somebody there? And then, well, maybe we can find something up. Yeah? Okay. So today, thank you for having me in this lecture series, Aki. I want to talk a little bit about the art and science of cycling. Now, there's a motto in this talk, and the motto is that everyone knows how a bicycle is constructed, yet nobody fully understands the operation. And with constructed, I mean a bicycle is 2 wheels and a steering assembly, right? That's it, single track vehicle. And with operation, I mean, how do you balance that thing? Because at 0 speed on a bike, you fall over. But given some forward speed, it's sort of easy. It's an acquired skill, but... And now the word nobody is interesting, because I've been working now for more than 20 years on bicycle dynamics and control. And I include myself in the nobody. So it's an intriguing system. I could not have done this alone. Most of the work, of course, at TU Delft, my alma mater. I did an internship at Cornell University in the US. That's actually where my research started on bicycle dynamics and control during that sabbatical year at Cornell. During that sabbatical, my whole research on bicycles started. Coming back at Delft, I started a lab, and that grew into the TU Delft Bicycle Lab. And then another from UC Davis, another collaborators, but more and more as years went on. There are 2 key publications. One is the first one on the linearized dynamic equations of balance and steer of a bicycle, a benchmark and review. That's with the Proceedings of Royal Society. And I always feel that we are among good authors, because that's the journal where Isaac Newton published. So, I mean, how bad can it get? And then the other one is a publication on a bicycle can be self-stable without gyroscope and caster, and that's a publication in Science. And yeah, we were struggling to get our research in science, and everybody was always saying, well, bicycles, what's new? I mean, bicycles are more than 100 years old. What's new? Well, apparently there is something new, otherwise you don't get in science, right? Okay, let's do some observations. This is an old movie. I'm an old man, so this is an old movie. Jour de Fête by Jacques Tati from 1949, and you see a postman who wants to rationalize, who wants to do things faster, so he's going to use a bicycle instead of walking. And you see the bicycle moving by itself. And everybody thought, of course, well, that's a trick, because everything is in movies is a trick, right? But it turns out, if you take an ordinary bicycle and you just give it enough speed, it will stay upright. And it will even go around the corner. Give it a little bit banking, it will gently go around the corner. So there's actually no trick going on. If you just take an ordinary bike, you propel it, bring it up to speed, you let it go, and it stays up. You call that stable. I would say that the bike is actually not stable, it's super stable. Because it's given its speed, it hit it sideways, oscillates, and an oscillation like that. So very, very stable, right? It even can have all these perturbations. So what is going on? What makes the bike so stable? Well, the bike in itself is very old. If you go back to 1820-something, then that's Carl von Drais with a hobby horse. With his feet he propels. There is a steering assembly. And then you see slowly there's pedals coming into play. And then you see the pedals are on the front wheel, and then you see the front wheel is getting larger and larger until you have a certain restriction, like this, right? The length of your legs. You cannot make the wheel bigger. And then there's a jump, and we see a chain drive, but it's a jump it's an evolutionary jump, because there's still this big front wheel, right? And then somebody said, well, actually you don't need a big front wheel, and to demonstrate he makes a small front wheel. It's also nice, and then you see steering assembly with a mechanism and then a bit of tilted axis, which sort of works fine. And then this is about the layout 1890 of the current bicycle. If you look outside, your bicycle will look a lot like this bike. And the hallmark is equal-sized wheel, pneumatic tires, and a chain drive. And that's like the modern bicycle. So what's interesting? Well, around that time of that modern bicycle, of course, scientists were also interested in this stable behavior at a given speed, speed-dependent stability. And on both sides, Whipple in the US and Carvalho in France were thinking of the problem and making models. They tried to make as simple as possible, to make it possible to do all these hand calculations, right? And the assumptions are rigid bodies, fixed rider, hands-free operation, everything symmetric, knife-edge wheels, point contact, so idealized contact, what we in a very fancy world call non-holonomic control. So there's no side slip and no frontal slip of the wheels. No friction or propulsion. And if you add up all these modeling assumptions, you end up with a system which has 3 degrees of freedom. I mean, the bicycle can lean, it can steer, and of course it can move back and forth. So those are the 3 degrees of freedom of the system. Note, by the way, that if you look at these assumptions, that there's energy conservation going on. I mean, there's no friction, no propulsion on flat level road, idealized contact. So energy conservation. And now you have to think back of that video where we did the perturbation experiment, where we hit the bike, it oscillated, and the oscillation died out. But that's sort of contradictory with that we say there's energy conservation going on. So on the one side you see then motion, on the other side you see energy conservation. So what's going on? I will address that later. Now with the 3 degrees of freedom, that's true. However, the model for a bicycle has about 25 parameters, and parameters being like the wheelbase, the trail, the distance, the contact point is behind the steering axis, the head angle, the mass of the wheel, the 2 wheels, the rear frame, the front frame. These are the parameters, about 25, meaning that The family of bicycles is big. So you can make all kind of contraptions. And here in the bike shed where you, at the entrance, as a staff member you can get in. There's one of these bikes, it's a very elongated bike, like a recumbent bike with a fairing even. And, but you can also do different size wheels, and we have all kind of family members in this family of bicycles. We are interested in the stability of motion, and in particular we are interested now in the stability of the straight ahead upright motion. So what we do, we linearize our equations of motion about that steady motion ahead. And then when we linearize, we get three linearized equations of motion. And the most simplest one for straight ahead is the last one about that speed. It says v dot is 0, or meaning the forward speed is constant. Up to the first order, forward speed is constant, simple. And then the other degrees of freedom, the leaning and the steering, so that's phi and delta. Phi, the leaning of the rear frame, and steering of the front frame relative to the rear frame. Then we see a coupled set of two second order differential equations. And it's just Newton, right? It's just mass, and these are forces. But I pulled the forces on the other side of the equation to get a nice differential equation. But it's just mass times acceleration is forces. And what are the forces? Well, first of all, these are the inertia forces, of course, with here some numeric values. Well, for the leaning, a high number, of course, because you have the mass and a big bike. And for the steering, you have a small number, because the steering assembly is not so inert. It's very light. And you have a coupling of the terms. Then we have some sort of damping term, which is proportional with forward speed, v. And the damping is very strange. It's not asymmetric. It's not zeros on the diagonal. Very strange terms. Let's move on. Then we have stiffness. Well, one of them is gravitational stiffness, this guy. And that is simply like a double pendulum. 2 degrees of freedom, gravity, it's inverted pendulum. So two of these bodies together, and it's highly unstable. So we see big, compared to the diagonal, big negative numbers, unstable pendulum motion. And then we see a term which is proportional to forward speed squared, and that has to do with cornering, because there are only entries for the delta and not for the phi. It has to do, if you go into a corner, you get what they say centrifugal or centripetal forces, and those forces exert torques and forces on the system, so that is a contribution. Well, we are interested in the stability of the motion, so we do the usual trick. We assume exponential motions, we form the characteristic equation, and since it's 2 second order differential equations, we get a 4th order polynomial. And of course, speed, we find speed interesting as a parameter. You could also take wheelbase or something else, but speed is interesting because at 0 speed it's very unstable, and given some forward speed, it shows stability, right? Well, we solve this characteristic equation for various forward speeds, and then we plot these eigenvalues as a function of forward speed. So here we have a graph. On the horizontal, we see the forward speed in meters per second, and on the vertical, we see the eigenvalues of the system. So they characterize the motion. So let's start at 0 speed. We have 2 plus and 2 minus. Well, it's like AB and minus AB, and it's like with an inverted pendulum, right? The thing is highly unstable, 2 positive eigenvalues, and of course also the 2 negative one for the time reversal. But then when speed increases, we see that 2 of these real roots, the blue one, they coalesce and they form a imaginary pair, or meaning that after this speed, suddenly we have an oscillatory motion going on, because when we have an imaginary eigenvalue, the solution is e to the power imaginary, that's cosine and sine. So we have an oscillatory solution here. But it's still unstable. We see the real part is positive until a certain speed. Then suddenly the real part of this oscillatory motion becomes negative, and apparently this oscillatory motion is then stable, exactly as we saw in the video. Then there are 2 other roots which are negative, so apparently very stable. Well, the very negative one has to do with steering. It's what we call the caster mode. If you have a non-zero steer angle and you are moving forward, then the wheel immediately aligns to a zero steer angle if you do nothing, so very stable. And the capsize mode is, there's almost no steering going on. The bike is slowly falling over. Well, here it's not falling over because it's negative, popping up. But here it's becoming mildly positive, very small number, meaning that you're, as a ship, you're capsizing, you're slowly falling over. But it's almost not noticeable because of the time scale. The eigenvalue is a small number, so before something doubles, it takes 10 or 15 seconds. So a lot of things happened within those 10 seconds. You see also in the diagram that there in this region, especially in this gray, but in this region, the bike is self-stable, apparently, just as we saw in the experiment. So the model explains what we see. Here we do unstable speed. We do a full multi-body simulation, and you see you start with some small perturbation, and it grows, and you fall. This is actually what happens when you learn to ride a bike. You don't understand the system so well, you go slow, then you're not so stable, you start oscillating, the oscillation grows, and you fall. So what do? You just speed up, right? So you go into a stable speed region, either your parent pushes you, or says, go faster, and yeah, as we see in the car park, here too in the simulation, there's an oscillation, and the oscillation is dying out. So even that full nonlinear simulation demonstrates that the linearized equations predict pretty well what is going on in real life for this bike. Remains the question, of course, about, but where does the energy go? Because it is an energy conservative system. So I put that question in your head now. You've seen it, there's oscillation, oscillation dies out. Think about where the energy goes. I'll come back later to that. Bicycle self-stability. So self-stability, how does that work in the bike? I would call it like an automagic control. I have no clue, actually. Now, to understand how the bike controls itself, maybe if we can look at how do we balance a bike, right? So how do you balance a bike? What do you do? Any ideas? First question, do you bike? Yeah, bike. Is there anybody in the audience who does not bike? Exactly, so everybody bikes. So you should know what you do. What do you do to balance?
I move my body.
You move your body?
Side or
Yeah. You stay on the saddle or you get out of the saddle or what do you do?
No, while bicycling, I stay on the seat.
Yeah, but then you move.
Yeah.
Steering? No steering?
Yeah, also.
Oh, you do steering. Okay. Steering to go somewhere or steering to balance?
I was thinking about.
Exactly. Well, that's the whole thing. If you ask yourself, like, how do I balance, then actually, I don't know, right? That is usually, it's unclear. So let's take a simpler problem. How do we balance an inverted pendulum on our hand? Now, do we have a long stick here? So we used to have these pointer sticks, okay?
Think of it behind that green screen. Probably there. Use eyes hide there.
No, it's not there. No.
It's here. Close it a bit.
Ah, yeah, thank you. Kiitos. Okay, so how do I balance this stick? Well, watch what I do. First of all, I observe, right? So if the stick falls to the right, I move my hand to the right. If the stick falls to the left, I move my hand to the left. So I move the support point such that the support is under the center of mass, which is approximately here, right? So if I look at the center of mass, of course it's 2 degrees. Okay, so that is the trick. So now we know how to balance a stick. So probably we also balance a bike like that, right? So an inverted pendulum by accelerating the contact point. In a bike, it's a bit difficult to move the contact point because then you have to move earth, right? And that takes some effort, I guess. However, In a moving bike, we have a steering assembly. And imagine you are moving forward and you steer to the left. Then your contact points go to the left, right? Or if you move forward and you steer to the right, your contact points go to the right. So in a moving bike, with a steering assembly, you can move your contact points laterally. Meaning that if I fall to the left, I have to steer to the... Which side? To the left. That sounds strange, right? So you fall to the left and then you steer to the left to get up. And that's exactly what happens when you learn how to ride a bike. You fall to the left, you steer to the right, it even gets worse, right? So it's an acquired skill. Question?
We have proven that the bicycle is stable by itself, then why we don't need control now to make it stable? So we are only talking about the speed before the stable part, or?
Correct. Yeah, I will repeat the question for the audience in the stream. So the bike is self-stable, so why do you need control to balance it? Well, if you looked at the diagram, at the slow speed, it's unstable, right? So to start cycling, you need some control to keep it upright. And for that reason, you need at least that control. Moreover, if you look at the self-stability, maybe it's just a marginal stability region you're in, and you need some more control. So you need to know, how do I get back to my point of attraction, being that upright motion? Does that answer your question? Yep. Okay, so again, so we balance the bicycle by steering into the fall. If you fall to the left, you steer to the left. If you fall to the right, you steer to the right. And that's how you get up. That's the whole mechanism. It remains the question, of course, why is the bike so smart that it knows to steer into that direction the right amount and the right time? Well, first of all, let's see, is that really true, that you have to steer to the left to stay upright and steer to the right? We have students at Delft, and in those days they used Lego Mindstorms in a project with Megatronics. And with a Lego Mindstorm, so you have Legos, you have motors, you have sensors and a computer. So you have those components, and then they usually build a walking robot or something like that. But Joep Mutschaers, he was a student, and he was a motorcycle enthusiast, and he thought, hey, cool, I can make a motorcycle, because I have a propulsion motor, I have a steering motor, I have a sensor, sensing that the thing is falling over, and I have a computer here. So he was devising control programs to keep it upright, but it didn't work. And he thought, I'm a motorbike rider. I know how I balance. I mean, I can ride a bike. Why can I not get the thing working? And he had all kind of control schemes in the thing, but it didn't work. He wanted to do his internship in Switzerland. He was already late, so he was in panic. And then somebody said, well, in the back there's this lab, the bike lab, Schwab, you should ask him, he probably knows. So Joep came into my office, and I said, well, balance your bicycle, steer into the fall, Joep, very easy. Let's see, what do you have? You have a steering motor, it's probably a DC motor, so the amount of voltage you put on it is proportional to the amount of torque you apply to the steering. Okay. So we know what the actuator is. You have a sensor. If you sense the lean rate, you're falling over. That's a nice sensor. Then that should be enough to feed back to your steer motor voltage. So if you apply the controller more, steer motor voltage is 8 times lean rate, or -8, or 80, or -80. You have to fiddle. I don't know how big the gain should be. And you have to fiddle with the sign, because we never know about plus or minus. Then it should work. And then Joep was standing next to me and saying nothing. So I said, Joep, what's the problem? Well, it's only one line of code, Professor. I said, yes. So Joep went away, and I think it took 5 minutes. And I think this is the living proof that how to balance, you have to steer into the earth. And why is it so oscillating? Well, there's play in the system, and it's Legos, it's a bit wacky, right? But it works. You can keep it upright. Okay, and if we look at the video, you see it falling and then steering, right? Falling and then steering. So we observe that same mechanism, steer into the undesired fall with the bike, self-balancing bike. Remains the question is, why does the bike do this, right? Where is the intelligence in the bike? And then people say, well, it's obvious. You have this front wheel, and it's rotating, and it's like a gyroscope, and we know gyroscopes can be very stable. You can get your position in space. Those gyroscopes helps you. They're like an inertial platform. So yeah, it's a gyroscope which makes itself stable. And if you check the numbers, so the wheel is rotating in this direction, so there's this rotation vector. Then the bike is falling over, that's the rotation vector of this. Then, yes, you get a torque in this direction, meaning it's steering into the fall. So it does, the signs are right. However, people say, nah, this effect is so minute, that couldn't be true. The whole trick is, of course, in the geometry of the steering assembly. You see this axis, the steering axis hits the ground, and then the contact point is behind the steering axis. And it's just like in a caster wheel, it's underneath your chairs and so on. That caster wheel follows you everywhere, and if it's tilted, it makes sure that the steering makes it upright. So yeah, we have two camps actually, like the left and the right, or the Republicans and the Democrats, or the snitches and the creatures. So who is right? Now we can vote, of course, but we can also try and use science instead of belief. So let's go to the gyroscopic effect. So the explanation of the gyroscopic effect was already from Klein and Sommerfeld in 1910. Felix Klein, famous from the Klein bottle. Arnold Sommerfeld, nominated 81 times for the Nobel Prize. I'm still waiting for the letter, and probably Aki too, right? And then Fritz Noether, the brother of Emmy Noether, who did this volume. Now, why did they wrote about the bicycle? Well, they were in gyroscopes, and they wrote a 4-volume book, and every volume is about this thick. So in total, on your shelf, you have so many books, 4 volumes, about the theory of the gyroscope. In German, Theorie des Kreisels. And in book 4, they have all kind of applications. And of course, when they see a bike, they say, gyro. So immediately they started their study on what is the effect of the gyroscope on the bike. They knew their classics, so they knew about Whipple and Carvalho, and they say, here we are interested in the gyroscopic effect, and we will show what Carvalho and Whipple did not do, that if you leave out the gyroscope, the whole region of self-stability will disappear. So it is the gyro which makes the thing stable, indispensable. So they say the stability of Whipple made possible solemnly through the gyroscope effect. However, my friend and colleague Jaap Meijaard meticulously went through the whole calculation, and then he said, there are actually 2 sign errors in their reasoning. And if you fix the 2 sign errors, then the reasoning is not clear anymore that if you kill the gyro, it's always unstable. Other factors are also in play. However, note that after 1910, everybody was copying the result of Klein and Sommerfeld. Oh yeah, the bike is stable because of gyro. Debunked, right? Not true. What is the other team? Well, the other team says, no, it's a geometry here. It's how the contact point is behind the steering axis. It's this tilted steering axis. And this is Jones in the 1970s. He's from Cambridge, PhD in chemistry. And then, well, he knows his classics too. So he knows Klein and Sommerfeld. So he mounts a counter-rotating wheel next to the normal wheel. And then he says, oh, mommy, I can even ride without hands. Very stable, no problem. So debunked this whole gyroscopic effect. Then he looks into the steering geometry. He builds a bike where the trail is very large, by flipping this front wheel. They have a large trail. And he builds one where the trail is actually negative, so the contact point is in front of the steering axis. And then he says, well, the bike is the trail is very large, then, oh, that's easy to control, I can ride without hands. Where the trail is negative, where the contact point is in front of the steering axis, he says, it's horrible, it needs a lot of control, and unstable, cannot ride without hands, so the trail is the magic thing. He goes into a calculation where he used potential energy to prove his point. He makes diagrams and he shows, oh yeah, when it's positive it's stable, when it's negative it's unstable. However, if you correct his equations, because potential energy for a stationary bike is identical to potential energy for a moving bike. Nothing changes, right, for the potential energy. So if we correct his equations, his reasoning with the dynamic equations of the bike, then we get an extra term, and then it's not so obvious that the trail is the dominant factor for self-stability. So, debunked again. So it's not gyro, it's not trail. So what makes a bike self-stable, right? Well, you go back to the equations. You have your 25 parameters, and you can express your characteristic equation. All these coefficients are in itself functions of the entries in the linearized equation of motions, which in itself are functions of these 25 parameters. Then for the stability, you have to form the Routh-Hurwitz criteria, so you have to form these 6 criteria, and then all these 6 expressions, given a forward speed, should be positive. Now, if you print that out, do symbolic computing, then I need more walls than the University of Lund has available to print out the equations. So it's undoable to find out which parameter makes it stable, yes or no. Okay, so then what we do, we make it simpler, the problem. We say, if they say gyro and trail is important, well, let's make a bike with no gyro and no trail and see if that bike can be stable. Right? So we call it a 2-mass skate bike. It has only 8 parameters. So the bike is on skates, right? Because there are no rotating wheels. Now the Dutch are very good in skating, so we should be able to manage that, right? There is no trail, so the steering axis really hits the ground in the contact point. We only have 8 parameters because we simply take point masses, right? And then for these 8 parameters, 8 non-zero bike parameters, you're able to form these equations and stitch from one to the other. And then on the left, we can find conditions for stability. We say if the front mass is within this region, it doesn't matter what the masses are, it's always stable. And if it's in this region, it's conditionally stable with some expression. But anyway, we find conditions for which, in this configuration, the thing should be self-stable. So no gyro, no trail, and it's self-stable. If we look at the diagram, so horizontal forward speed and vertical eigenvalues, yeah, the theory predicts from a certain speed on this thing is self-stable. Next step, we build that machine, right? So we make it. Of course, with point masses here, we do not have skates, so we have counter-rotating wheels. And so it's about 99.5% gyro-free with those counter-rotating wheels. That's from measurement. And we made the trail a little bit negative. We made it negative because in reality the contact region is finite. You always have a finite length. And we want to be sure that the reviewers would not say, yeah, but you have finite, and if you do 0, you still have a trail. No, we make sure that we definitely have 0 or even negative trail. Then we built the machine. This was theoretically. Now this was the machine measuring everything, putting it in the model, and then we still found comparable behavior, right? A bit different eigenvalues, but still self-stable. Then the proof of the pudding is to eat. So we go to a gym, we propel it forward, we release it, it stays upright, stable, right? Until it hits the ground, yeah. And then we do it again, we propel it, and then we hit it sideways. You see an oscillation dies out, and it's upright. So clearly stable, without gyro, without trail. And that was actually also the topic of our paper in Science. A bicycle can be self-stable without gyro or caster effect.
So you can publish in the Science even when you're coming from the mechanical.
Mechanical engineers can publish in Science, yes. And you can even publish on bicycles in Science, which is even a bigger challenge. Now, remains, of course, why is it self-stable? Well, you all have the answer, right? Because to be stable, what do you have to do? You have to steer into the undesired fall. So apparently this machine, this contraption, steers into the undesired fall. Now, bear with me. You see that the mass of the steering assembly is in front of the steer axis, a little bit in front, meaning that if we tilt the bike, it will start steering in the direction of the tilting, right? Why does it steer the right amount at the right time? Well, that has to do that this mass is higher than this mass, so this one is probably quicker than this one is in falling, and as we also saw in this conditional stability, right? For some mass, for some mass it works here, some mass is too far out, there's some condition on the relation of the masses. But apparently that's the whole trick. So in a nutshell, the mass distribution makes this thing self-stable. So to get back, why is a bike self-stable? Well, because of a number of reasons. Well, first of all, it's self-stable, then it must steer into the undesired fall. That's no question about that. And how does it do that? Well, it can either be gyroscopic effect, or it can be a trail, or it can geometry, or it can be mass distribution. So it can be a dynamic effect from the gyro, it can be a geometrical effect, forces from the contact points, or it can be a mass distribution thing. Question?
Yeah, is this the reason why a motorbike is getting unstable when you put too much load on the back? So the center of mass is going behind the center of mass of the steering?
Apparently there, when you play with the mass distribution, the dynamic behavior changes. And it could make from stable, you could end up in unstable. Yes, absolutely. Yeah. And also when you take somebody on your bike on the back, but usually they move also around, so that makes it even more complex. Yeah.
But I mean, sometimes when you have much load on the motorbike
Yeah.
and you hit some
Yeah.
stuff on the ground, the steering is like
Yeah.
wobbling around. And
Yeah, that could also be another instability. So we have not talked about that here. What we talk about the instability here is the weave mode. Maybe the instability you're talking is the shimmy mode, where you have a very high frequency steering oscillation.
okay.
And the shimmy mode can occur when there's play in the system or when we have flexible tires. This model has no flexible tires. If we add flexible tires, there's real tires to the model, we can predict this shimmy. I can even talk a little bit about the project of that shimmy. Yeah. Yeah. Okay. Rider control and handling. Given the time, we go until 15. We have still 50 minutes, right? So I'm going to skip the rider control and handling. If you want to talk about that, come to my office. I want to talk a little bit about applications, right? Or in other words, what is the relevance to society for this research? And that was one of the big things we were struggling with, because the moment we got this publication in Science, so first the Royal Society, then Science, so it's a whole building block, and then I thought, well, every grant proposal I write will be granted, right? I mean, who can object against science publications? Well, every application I did was rejected. Why? They said, well, bicycles, old. What's the problem? There's no problem. Everybody rides a bike, there's not really a problem, so where do you want money for? And then finally our luck was that people were dying on the bike. So what is going on? If you look at seriously injured or death in traffic, then you see with the years, the number of deaths and seriously injured in traffic with cars is going down. It's what we call mission zero. We want 0 deaths in traffic. And that's a good thing. But if we look at the bicycle, and in particular in the Netherlands, we see that the number of deaths and seriously injured are rising and rising every year. Of course, that larger amount has to do also with exposure. People are getting older and they're staying longer on their bike, but still it's a bad message. Even more when you look at who is getting seriously injured, and it's elderly. 80% of them elderly. So that's not good, because a seriously injured elderly is usually within 3 years mortality. So if older people breaks a hip, he will not recover. It usually goes bad. An interesting feature of those accidents is that 75% is single vehicle accidents. So they do not get run over by a truck or a car, they just fall over. And in this falling over, the stability of the bike plays a role. So suddenly there was an interest in this dynamics and control of the bike. So what did we do? Well, for the consumer industry, we looked at safety of e-bikes and elderly. There was a big question. Elderly on e-bikes, are they dangerous? Because, oh, they go so fast, it's dangerous. Well, we did an in-depth study with a large number of participants, either on a normal bike and an e-bike, with distraction, all kind of things. It turned out that elderly on an e-bike are more safer than elderly on a regular bike. Because on a regular bike, they go too slow, and they don't merge with the traffic. And on the e-bike, they go with the flow. No problem. Then in sports engineering, we worked with an elite team to look at the optimal power distribution in time trial. For the consumer industry, we investigated the shimmy behavior, what you mentioned, the rapid oscillation of your steering assembly. That becomes suddenly a problem with the electric assisted bikes and the step-through frame, which is more flexible, and with a battery on the back. Then for the consumer industry, we also looked at a system called Steer Assist, where we have a motor in the steering assembly and sensors, which when the bike is falling over, is just steering into the fall. So it's an active system to stay upright, and it helps you in balancing. We looked at tires, because there was almost nothing known about cornering and camber stiffness of bicycle tires. Nobody had numbers, so we started to measure our own. Within sports engineering, we looked at the optimal team time trial. That was with Team Alpecin with Tom Dumoulin, and the first time in the Giro, it was executed, and everybody thought, oh, that team of Tom, they're not so good in the time trial. But, well, we didn't become first, we didn't end at first, but still we were among the first 3, and everybody said, hey, why did they do so good in the time trial? It was a super cool project. Because, well, the team time trial is you have, say, 8 elite cyclists, and they start, and then the finish time of the 7 of number 6, that's their time. So this whole group has to do this, the trial, this distance, and of course you change position all the time. Somebody's at the head, and then after a number of seconds he falls down, and then the next one. And to us, this looked like engineers, like the super nice optimization problem. Because you have 8 motors, 8 different motors, and with 8 different resistance. One is big, other is small. And so everybody has his own power management system, optimal thing going on. And then the drag is also dependent on the position. Because if you have some drag and you're at the 3rd position, the drag is different than at the head, right? You have these slipstreams and so on. So beautiful for optimization problem. So we programmed the whole thing, and then we had a nice solution. So we said, well, you start 1, 2, 3, 4, 8, and then the first one does 6 seconds, goes back to position 3, and then number 2 stays there for 12 seconds, go to position 6. So we had a whole scheme worked out. And then they said, the team, we're not going to do that. I said, you're not going to do that? this is the optimal one, you're going to win. No, we're not going to do that. It's impossible to execute. We cannot communicate. The only thing is they have one piece of ear, and the coach is yelling in all these ears together. Right? There's only one channel going on. We cannot do that. So we tuned down the whole system that the head position is always going to the back, and then we came up with a new schedule, and the team did pretty well.
Ready?
We're also interested in doing experiments in a safe manner, and therefore we want to build a bike simulator with visual feedback. There's Oculus Rift going on. You can pedal, you can ski, you get feedback on the.
Can you do a shoulder check?
I call
Great.
this one the bike simulator with a bucket because it's not linear, and you get complete linearity most of the time. So we are still busy in developing. For sports, we made one which can lean. So this is a bike simulator where we got rid of the wheels, but where we just move the contact points according to the bicycle kinematics, meaning if you have a given speed and a certain steer angle, the kinematics tell you how fast the contact points should move. And this is actually a beautiful machine because it just behaves like a bike. It's just a bike and it's stationary indoor. However, with this setup, you cannot really do experiments with elderly and fragile people and so on. So it was more for the sports application. We're now building a bicycle which is stationary but which can lean and steer and propel. So we have 3 modalities of power. We can actuate the limb also, so we can make it very stable. The visual feedback for this is under development. In sports, we also look at skills. Why is one essential and another one not? Follow the guy. Follow the guy. Always stay behind. Like other ways. With the Olympic team, we were able to build the new track bicycle for the track cycling team, for the Olympic track cycling team. And there was a very multidisciplinary thing. It was aerodynamic people, it was structural dynamics people, and it was us for bicycle dynamics and control, because some were complaining about the handling. It was funny, I don't know if I have more, I don't want to talk about this. Yeah, I want to talk about the new bike for the track cycling team. As engineers, our first observation, so this is the old bike, was they don't fit the bike. The bikes are too small. So as an engineer, we immediately said, oh, the bikes have to be bigger. But the riders said, oh, we don't want a big bike. Why? Oh, it's maybe more weight or whatever. But we were able to design actually bikes such that the riders fitted. Because the idea was the rider is a motor, and there's resistance, but there's also power, and we want the maximum power, meaning they have to have the maximum, the posture where they can deliver maximum power. So we took them first to this bike fit thing, their initial position, and then by measuring and adjusting, we found an ideal position where they can deliver a lot of power and they are in the good aerodynamic position. Then the result was that for every rider, we've had an individual setup, meaning we had to have 3 different frame sizes, which became far too expensive for these carbon bikes. So we found a average frame size, and then we played with the cockpit by putting them farther away or changing that geometry. So we were able to fit them all on their bike. Same for the ladies, we did the same. Then there was an interesting thing on the bicycle dynamics and control. One of the riders was complaining about the bike he was riding. He said, it's very nervous when I'm in the corner and I try to accelerate. I have trouble staying between the lines. And when I ride my private bike, my Look, which is not allowed in the team, but they practice on their own bike sometimes, then I have no problem. So we said, okay, there's something going on with your dynamic steering. So the steering stiffness, or the dynamics of the steering, we can picture by, for a certain speed and a certain steering frequency, we can see what is the stiffness. And we saw in his initial bike that there's this really low point in the graph. And for the Look bike, it looked a bit like this. So the new bike were all designed with this dynamic steering stiffness, but just tinkering a little bit with the head angle and the trail. So that was the new bike where we changed his whole geometry according to have the same like in the Look bike. Well, and the test of the pudding again was here to eat. We were totally anxious, like, oh, hopefully the bikes will work. Because again, their first reaction was, oh, they're very big. Yeah, okay, trust me, I'm a doctor, it will work. And I don't know if there's people who follow track cycling, but they won a lot of gold medals. World records, gold medals, and no problem. So, any questions? I think we have 3 minutes for questions.
3 minutes for discussion.
Yeah. And don't hesitate, if there are any questions or discussions, step by my office or send me an email. Oh yeah, I had a question for you. Energy conservation.
You know, guys, when we discuss about the master thesis topic, I mentioned that it doesn't really matter what topic you pick. Each of the topics you can take any direction you want. This is a key example. So you can take a bicycle, and you can put it all the way onto, you can publish it in science.
Yeah.
That's something that is good to keep in mind. You know, pretty much anything you want, you can put it in very high level of theory, and you can figure out many things.
Yeah. And there's
Or
one.
you can take any topics and you can leave it in very
Yeah.
shallow.
But there's one important ingredient, and that is you have to collaborate. You always, working together is the magic trick. So reach out to colleagues and friends, try to form some consortium where you can work together. Why were we able to publish on the equations of motion for a bicycle? You would say, well, Whipple and Carvalho did it already, right? There were errors in the equation. We investigated all publications on bicycle dynamics equations. All publications until 1956 had errors in them.
Because humans have this tendency to make errors.
Yes.
It can happen.
Yeah.
And it's your responsibility to be skeptical.
Yeah. And then by working together, we had this triangle. So I had a colleague in the UK, Jaap Meijaard. In the US, Jim Papadopoulos had been working on it, formed the equations, and I came with my sabbatical at Cornell, and I had my own software for deriving equations of motion. And then we compared, the three of us, the results, and that's how we said, well, these must be the equations, and these must be right. And then holding all the others against the light, wrong, and then 56, Döring from Germany was the first who had them completely right. And that was that first paper, of course, the benchmark. Yeah. But I had a question for you about the energy conservation. You saw this damped out motion, but there is no damping. So how can we have a damped motion when there is no damping? Where does the energy go? So there's energy in the lateral motion, and that disappears, or what happens with the lateral motion energy? Any ideas? Yep, speed increases. Although I said the speed is constant, yeah, that's linearized equations of motion, but in a nonlinear case, the speed will increase a little bit. And it's a one-way thing, right? If you, and it's nonlinear, it's an uneven effect, because if it starts moving to the left oscillating, it will speed up, and if it starts to the right oscillating, it will also speed up. So that's a demonstration. That's a nonlinear effect. So it will speed up a little bit. Yep, correct. Okay. I think then this ends the presentation.
Gonna click this one. Where's OBS?
Yeah, let's get there.
I cannot close it here.
No, I can do it. I can do it. Just kill it.
Yeah, just kill it.
Yeah.
So I will see here, because I see there.